Practice Test A, Objective 6, has us applying Hess's law of heats of summation to find enthalpy change for chemical and physical processes. Our first question says, calculate the heat change, that's delta H, for the formation of nitrogen monoxide from its elements. We are being asked to turn those words into a balanced equation, and that balanced equation then becomes our target equation. We are forming nitrogen monoxide. To form, we need to point at it, creating a product of nitrogen monoxide. Listening to those prefixes and letting that guide our NO for nitrogen monoxide. And the elements that it's built from both belong to the Lucky 7 diatomic club. Nitrogen and oxygen will be written in molecular form N2 plus O2. And of course, to balance our equation, we'll need to have 2 units of NO. The target equation we are being asked to build will be N2 plus O2, forming 2 units of NO. We'd like to know the heat change for this equation. What is the value of delta H? What we do know are the following elementary reactions. In our first equation, I'm reading 4 units of NH3 react with 3 units of O2 to form 2 units of N2 plus 6 units of water. Its delta H is given as negative 1530 kJs. Our second elementary reaction, 4 NH3s plus 5 O2s yield 4 NO and 6 H2Os. We are being asked to use these 2 elementary reactions, equation 1 and equation 2, so that somehow when we add them together, simplifying what we can from the left and the right, that it indeed forms the target equation that we just wrote in that combination pattern. The target is to build 1 unit of N's plus 1 unit of O's to produce 2 units of NO. For no particular reason, then it's written first. I start using my elementary reactions to find the first reactant in the target. Where do we see N2 written in our building blocks, in our elementary equations? Well, I notice in the first elementary reaction, I'm seeing it written, and it's in a unique spot. That's very helpful in determining what to do with that first elementary reaction. I notice that N2 is on the wrong side of the arrow as compared to my target. And I'm noticing that it's twice as big as I'd like it to be. I have a hunch that I'm going to flip the direction and I'll need to cut it in half. Again, my reason, I'd like to have 1 unit of N2 on the reactant side, but where I'm seeing it is on the product side, and it's twice as big as I'd like it. If I flip it and cut it in half, I might have just what I need. Again, I'm not showing work yet. I'm just simply thinking out loud, brainstorming a strategy. The next reactant is the O2 in the target equation. What I'm noticing is the O2 appears in both elementary reactions. It's not very helpful if it's appearing in both. I'm not going to gain insight into what to do with that second elementary reaction. I'm going to choose to ignore that for right now. I'm not finding it in a unique place. More interesting is the placement of our product NO. I'd like to make 2 units of NO in our target equation. Where might I find NO in the elementary reactions? Well, I'm finding it in the second equation right here as the listed of the first product. I like the side that it's placed on. It's on the product side as I desire it to be, but 4 units of NO is twice as large as I'd need in my target equation. I only need to produce 2 units, and I have 4 in the target. Again, thinking out loud, I'm going to divide this by 2, or cut it in half, whatever you think of in terms of being easiest for you. Cutting in half, dividing by 2, we'll need to do both of that. Flip the first, cut it in half, and then simply cut the second one in half. Let's see what that gives us. Let's rewrite the strategy so far. We decided in our first elementary reaction, rewriting it in the opposite direction, taking only half the amounts. So the original products now become the reactant. We had written 2 units of N2. Let's cut that in half. We'd now be left with 1 unit of N2. Plus, we started with 6 units of water. Cutting that in half gives us 3 units of H2O. Then we see the yield sign. On the original reactants, now writing M on the product side, we started with 4 units of ammonia. Cutting it in half, we're down to 2 units of ammonia, NH3. Up here, we started with 3 units of oxygen. If we cut that in half, let's write that as 3 halves of O2. The delta H for this new equation will be found by looking at the first value given, negative 1530. Since we flipped to the direction, we need to make it positive, and we also cut it in half. We need half the value. Let me hit on the calculator. 1530 divided by 2, and I find that to be 765. Half the amount and the opposite sign give us the new delta H for our elementary reaction. The second equation, we decided to leave the direction alone, but to cut it in half. We started with 4 units of ammonia. Cutting that in half leaves us with 2 units of ammonia. The next reactant written is 5 units of O2. When we cut that in half, we would write that 5 halves of O2. Leave it in the fraction form. The next product listed is 4 units of NO, but cutting that in half leaves us a net of 2 units of NO. And finally, 6 units of water cut in half gives us 3 units of H2O. The delta H for this new equation would simply be half the amount of the original value. Let me hit that. 1170 divided by 2 is 585, still remaining negative, but half the amount. Hess's law of summation. If we add our 2 equations together, simplifying what we can, let's prove to ourselves we indeed have made the target equation. What could cancel? I'm noticing in the first reaction I made 2 units of NH3. And in the second equation, 2 units of NH3 are being used. A product on one side cancels the reactant on the other. The ammonias are gone. I also notice in the first equation I have 3 waters written on the reactant side, and in the second equation I have 3 waters written on the product side. 3 H2Os on the left will cancel with 3 H2Os on the right in the next equation. The waters are gone. I'm also noticing O2 appearing on both sides. On the first equation, we have the amount of 3 halves. In the second equation, we have the amount of 5 halves. That can be simplified. 5 minus 3 is 2. 2 halves is equivalent to writing 1 unit of O2. If I take out the product side in the first equation, 3 halves O2, and I simplify with the 5 halves that was written, 5 minus 3 would give me 2 halves. 2 halves is equivalent as 1. And look what we've done. We have taken N2 plus 1 unit of O2 to form 2 units of NO. And that indeed is our target equation. The only thing left to do is to add the new values of the delta H's. Positive 765 plus a negative 585 gives me a total value of positive 180 kilojoules. The value for our target equation we were solving for, 180 kJs, an endothermic value. Let's look next at practice test A, the second question with Hess's law. Our target equation has us looking at P4O6 as a solid plus 2 units of oxygen O2 forming P4O10 in a solid phase. This is what we would label as our target equation. We have 2 elementary reactions to build our target. Elementary reaction 1 has P4 as a solid plus 3 units of O2 as a gas, forming P4O6 solid. And that second elementary reaction, P4 solid plus 5 O2s yields P4O10 solid. For no other reason than it's written first, in my target equation, I generally start looking to find my first reactant. Where might I look to find the first reactant, P4O6? And again, just start skimming through the elementary reactions until you locate it. Here I have it at the first equation at the end, listed as a product. What I like about it is that it has the correct number of units. There is a 1 which matches the target value. We need a 1. But what I don't like about it is the side of the arrow it's on. In my target, it appears as a reactant, but in the elementary reactions, it's appearing as a product. Thinking out loud of a strategy, I think I need to flip the direction of the first reaction. I notice the second reactant is oxygen, O2. I'd like to end up with 2 units of O2. But the O2 appears in both elementary reactions. It's not in one unique place. The O2 is not something I would choose to make a decision on what to do with these elementary reactions. Let's instead focus on the product P4O10. P4O10 appears as a product in the second equation. Again, I'm going to ignore the O2 because it's not in a unique place. The P4O10 is unique. It's uniquely placed as a product in the second elementary reaction. Here's what I like about that. I have the correct number of units. In my target, I need to produce 1 unit of P4O10, and the target equation has just 1, so does the elementary reaction. And it's on the correct side of the arrow. That tells me I should leave this alone. So far, I've just been sharing a strategy. Let's indeed prove to ourselves that by flipping the first, leaving the second one alone, we have indeed built our target equation. Let's rewrite elementary reaction 1, but flip its direction. The original product, P4O6, now becomes the reactant. And the original reactants now are on the product side. P4O6 points at P4 plus 3O2. The delta H for this equation, simply flipping the sign, it now reports a positive 1640.1 kJs. We decided to leave the second elementary reaction just as it appears. I'll simply rewrite P4 plus 5 O2s make P4O10. The delta H remains the same value, negative 290, negative 2940.1 kJs. If we indeed add these together, simplify what we can. I notice that P4s are on opposite sides of the arrow, a product in equation 1, a reactant in equation 2. They will cancel one another. I also notice that on the right side of our first equation, I have 3 oxygens, and on the left side of the equation, in the second, I have 5. If I simplify, I can get rid of the 3 O2s, leaving me a remainder of 2. 5 minus 3 simplifies to 2 units of O2. And indeed, we have built P4O6, left over from that first equation, and 2 units of O2, the remainder of our second equation, forming the desired product of P4O10. When I add together elementary reaction 1, its heat, with the elementary reaction 2 of its heat, we'll find our final answer. So let's hit positive 1640.1 plus a negative 2940.1. I get a value of negative 1300 kilojoules, an exothermic value. With Hess's law of heat summation, we are being asked to find the enthalpy change of what we call our target equation, given the elementary reactions to build from. What we're trying to do is somehow add the 2 equations below so that they create the target equation. And once we do that, we simply add their values of delta H to find the target. Whatever we do to the elementary reaction, we do the same thing to the target. IF plus F2 given IF3, its value of delta H provided. IF plus 2 fluorines give IF5, its delta H is provided. We have 2 building block equations to create the target. IF5 yields IF3 plus F2. I simply turn my attention to the first reactant in our target equation and start skimming through where I find the IF5 in the targets. I'm noticing that IF5 is given to me in the second equation, and it's a unique place. There is only one location of IF5. What I'm noticing is I have the right number, but it's on the wrong side of the arrow. I'm predicting that we'll need to flip or reverse the reaction for number 2. And when I do that, I know I need to change the sign. The second ingredient listed up here in the target is the IF3. IF3 appears uniquely in that first target equation. I like the number I have, and I like the side of the arrow I'm on. I bet we just leave that alone. Let's rewrite, finally showing the work we would be required. Leaving the first one alone, we'll just simply rewrite it. IF plus F2 yields IF3. Delta H has stayed the same at negative 390 kilojoules. When we rewrite that second equation, we'll flip its direction. IF5 now yields IF and 2 fluorines. Since we flipped the direction, the sign now is positive 745 kilojoules. I'm noticing here I can cancel out a fluorine, leaving me a net remainder of 1 fluorine on the product side of our second equation. I'm noticing here that IF cancels and leaves no net remainder. And indeed, we have created what our target asks us to find. We have IF5 yielding IF3 and 1 unit of F2. All that we need to do now is add those 2 values of delta H. Negative 390 plus positive 745 gives us an endothermic value of 355 kilojoules. The value for our target equation, positive 355 kJs.